wouldn't your red blood cells stop?
Yes.
So it started to clot, wouldn't it break down?
It would depend on how old those particular blood cells were.
Okay.
If you got lucky and they were just about to die, perhaps they would fall apart before you caused damage.
Okay.
If they were younger, maybe not. But because it's just one capillary, it's not that big of a deal. Where it can become a big problem is if you get something into your system that plugs a whole bunch of capillaries. Like if you get the bends, are you familiar with the bends?
Yeah.
The bends. What is it?
It's when you're scuba diving and you send too fast and the oxygen expands in your blood and it stops.
Yeah.
Flowing.
And so one thing you learn in chemistry is that as you go down, as your pressure goes up, as you go down the ocean, pressure goes up. So as you go down, more and more gases dissolve in your blood. If you come up quickly, those gases have to come out of your blood. If you go slowly, they just show up in your lungs and you breathe it out. If you come up too quickly, though, you get bubbles in your blood vessels. And so if you get a bubble here, you're probably going to get it in a whole bunch of capillaries. And so a lot of your capillaries are then clogged. And so you then have to go into a pressure chamber to bring the pressure back down, back up, but like you're down at the bottom of the ocean, to get the bubbles to redissolve. And then you very slowly bring the pressure back to the surface of the ocean. And so then that gas can be exhaled. This is just another diagram showing blood going through the capillaries. So as we enter the capillary, we get what's called filtration. So filtration is allowing nutrients and oxygen out of the capillaries. And then we get what's called reabsorption. And so we're bringing back in waste products and carbon dioxide. We'll talk more about this whole lymphatic fluid and lymph in the next lecture. So remember, what causes this blood to flow through all these blood vessels are changes in pressure. Things, not just blood, but everything, always flows from high pressure to low pressure. And so, if we have high pressure differences, things are going to flow faster. And so, if you have high blood pressure, the blood is flowing faster through your system. That's actually why we have high blood pressure. A lot of times, our body does it on purpose to get the blood flowing faster. In the short term, that's good, but we've learned for long term, that's bad. So when the ventricles contract, that is your pump. That is the pump that creates an area of high pressure in the heart. And then the further you get from that heart, the lower your pressure is going to be. If I take, let's say, a leaf blower, if you put your hand right in front of the leaf blower, you're feeling a very large pressure difference. But if I point it at Jessica in the back, she's barely going to feel it. Because the further away you get from that leaf blower, the less the pressure difference is. So the air is not moving as fast. Same thing is going to happen here. We measure blood pressure in millimeters of mercury. That is an actual scientific measure of pressure. We use that in chemistry and physics and things when we're dealing with gases. Blood pressure is also partially determined by the volume of the blood in your system. If you have a whole bunch of blood volume in your body, your blood vessels are already swollen. They're big because they have to hold a whole bunch of blood. And so what your heart does is it creates a pulsing sensation. When the heart beats, the blood vessels are going to have to expand because there's a burst of blood pressure. But if you have a bunch of blood in your system to begin with, your blood vessels are starting bigger. So they're maybe pulsing out here rather than pulsing down here. Part of the reason that as you get further and further from the heart, the blood pressure drops is because of what's called vascular resistance. It's just the resistance that created from blood and water flowing through a tube. You have friction between the water and the cells and everything with the walls of the blood vessel. Just because you're in a body does not mean you can avoid the laws of physics. If you have something moving past another thing, you're creating friction. And the more friction you create, the slower it moves. The slower it moves, the lower blood pressure that you have. Here, what we see is blood pressure as you get further and further away from the heart. And so we're in the aorta, which is the main artery. It is the main source of oxygenated blood coming out of the heart. And so we go from aorta to arteries, to arterioles, to capillaries, to venules, the veins, and then the vena cava is essentially the vein version of the aorta. There's almost all of the blood in your body returning to the heart is going to go through that. So here, we have a very high blood pressure, and we have very large spikes. Every time the heart beats, we're getting very large spikes, and the average pressure is very high. Once we get down into the arterioles, though, it starts to drop very, very quickly. That resistance is actually tied very directly to the diameter of a blood vessel. It's not a blood vessel that's half as big creates twice as much resistance. It's actually a cube. So if you have a blood vessel that is two times smaller, so half the size, you have 8 times the resistance. And so it drops very, very quickly. Once you get down to the capillaries, you have very low blood pressure. And then in the veins, there's very little at all. Once you get down into the veins here, you have almost no effect from the heart. There's no peaking. And actually we'll learn that this baseline blood pressure here is more or less not even due to the heart. There are other mechanisms in our body that are going to provide enough pressure here to keep it flowing. We have to keep it flowing, otherwise we back up. And so then this blood can't leave the heart. So we have a number of different ways that we can control this blood pressure. Number one, we can change heart rate. The faster that heart is pumping, the more blood is pushing through the blood vessels, the higher the pressure is going to be. We can change that a lot. Our heart rate can get very, very slow. It can get very, very fast. While we can't control it all that much, we can control it a little bit. That's stroke volume. We can actually control how much our heart is contracting. If it contracts more, it's going to push more blood. If you push more blood, you'll get higher pressure. This is not a fine-tuned system, and you can't control it all that much, but it is a little bit. Also, the vascular resistance, like we said, that's going to be controlled by how large your blood vessels are. Yes, as you go from arteries to arterioles to capillaries, by definition, you're getting smaller and smaller. But up in the arteries and the arterioles, we have systems, that smooth muscle, that can control how big they are.
So how does blood pressure medication work then?
So there are a number of different ones. The vast majority of them are going to slow heart rate. Vast majority of them are going to control that. Probably the next most common would be something like a diuretic, which is going to actually control blood volume. A diuretic makes you urinate more. When you urinate, that water came directly out of your bloodstream. And so if you're taking water out of the bloodstream, you're going to reduce blood volume. Yes?
Diuretics basically kind of dehydrate you, right?
If you have a normal hydration to begin with, yes, they're going to take you down lower. If you have too high of a dose, it may make you dehydrated. But our body is actually very, very good at maintaining blood pressure at low hydration. The people that walk around with bottles of water because they think they're going to die if they don't drink something every 15 minutes are making a bigger deal out of them, actually. So imagine that hose. If you put less water in a garden hose, it's not going to be bursting at the seams. If you put a whole bunch of water and you have a high blood volume, you're going to have pressure pushing out on that garden hose. Same thing in our blood vessels. The vascular resistance, if we all of a sudden have low blood pressure for any number of reasons, whether our heart is not working correctly, or this is actually probably the main way that our body maintains blood pressure when we don't have water. As we lose water, our blood vessels just get smaller and smaller. If we have less water, just make the hose smaller. You still get the same amount of pressure. And so we can change vascular resistance simply by constricting our blood vessels. If we drink a whole bunch of water and we have very, very high blood pressure, all we have to do is make the hose bigger. We decrease the resistance. Sorry. Yes, we decrease the resistance, which will make lower pressure. Yes?
So would diuretics be considered a vasoconstrictor?
Diuretics actually work directly in the kidney. So we'll learn about how that works. So the kidney actually, as the blood goes to the kidney, it takes more or less all of the water out, and then it decides how much to put back in. A diuretic makes the kidney say, well, I'm going to put very little back in. Most of it's going to go to the bladder. So we learned that the cardiovascular center is controlled by the medulla oblongata, right?
Yes.
Yes. Nobody's going to get that wrong ever, ever, ever for the rest of your life, right? And so the medulla oblongata can control the heart rate and the stroke volume, primarily the heart rate though. Primarily the heart rate. And we have some other factors that we can use to control that blood pressure. And so we're going to receive signals telling us what the blood pressure is, and then we can use either neural, meaning like nervous system, or hormonal, being endocrine systems, in order to change these two things. The inputs that it's receiving are coming from 3 different types of receptors. We learned about proprioceptors. What were they? That was one of the general senses.
Pressure? No. Balance? No. Okay.
Proprioceptors.
Sensory perception.
Proprioceptors are the ones that tell us where our body parts are located.
Oh, okay.
So, imagine I'm laying down. The most important thing in my body to get blood is my brain. Without my brain, the rest is useless. So, I need the correct blood pressure in my brain. If I quickly stand up, do you think it's easier or harder to get blood to my brain?
Harder.
Harder. If I'm laying down, you're just pumping it straight across. But if I'm standing up, you have to pump against gravity to get blood up to my brain. And so if I'm standing up, proprioceptors are going to tell my brain, my head is above my heart. You better increase that blood pressure. Yeah.
Just sitting down, the blood pressure increasing it
Blood pressure,
because you're like a
yeah, and so because your head is still above your heart, it's still the same mechanism there. And so sitting and standing aren't going to be that different from each other, but when you're standing, you're exerting yourself more. It's taking oxygen and stuff, my posture muscles and everything to keep me upright. And so I do need higher blood pressure. So if you stand up too quickly, there's a couple different things that are going to happen. Number one, you're going to use a bunch of oxygen in your blood in that split little second. But also, imagine water. Our blood is water, basically. If you stand up quickly, where's the water going to go? Down. And so after that split second, it's not the fact that your heart's not pumping, your blood pressure's not high enough, it's that you moved your brain away from the water, away from the blood. And so for a split second, your blood pressure is lower in your brain. If your blood pressure is too low to begin with, maybe for that split second, it'll be so low that you might faint. But if you're, yeah. So if you have a healthy blood pressure to begin with, when it drops for that split instant, it's still within a decent level, decent level, and so you're not going to faint. But if you're on the low level of normal to begin with, when you stand up, you may faint. We also have baroreceptors. Baroreceptors are just going to measure how large your blood vessels are. And so if my blood vessel is normally this large, and I drink a whole bunch of water, and so my blood volume is going to increase, it's going to make my blood vessel expand. The baroreceptors are going to notice that. They're going to notice that they got stretched because they're wrapped around the blood vessel. So if the blood vessel stretches, the baroreceptors stretch. So they're going to send a signal to the brain saying the blood vessels just got bigger. Blood pressure must have gone up. If blood pressure went up unexpectedly, the brain can compensate to bring it back down. We also have chemoreceptors that are going to measure the concentration of things like salt and glucose in our blood. And so if we don't have enough water in our blood, the salt concentration is going to be too high. Imagine you have a glass of salt water. If you let it sit out and have the water evaporate, the salt in there is going to get more and more concentrated. Because you're always going to have the same amount of salt, but you're going to have less and less water. Same thing happens in our blood vessels. If we continue to lose water, but don't bring in an equal amount of water, the salt water in our blood gets more and more concentrated. And the chemistry receptors are going to sense that. And if the salt gets too concentrated, we're going to know that we have low blood pressure because we lost a bunch of water. So we need to do something that may just be causing a thirst sensation. If you get thirsty, you drink something to replace that and get your salt water back to the right concentration. So this is what we just talked about. I'm not going to go back through it. So we said that some of this is controlled by the brain directly through neurons, through the nervous system, but some of it is with the endocrine system. So there are a few different hormones that can do this. Primary system is called the renin-angiotensin aldosterone system, or the RA system. You may have learned just the renin-angiotensin system.
I have not learned any.
Well, you're about to.
Go slowly.
It's not that complicated. We're not gonna make it that complicated. It actually is quite complicated.
It's not that complicated.
It is the complicated.
Actually, you know what?
So the kidneys are going to secrete a hormone, also an enzyme called renin. Okay? And renin, its purpose is to increase blood pressure. So your kidneys, like we said, they're the main filters for the water in our blood. They're going to sense how much water is coming through them. And if they know that there is not enough water coming through them, that you have low blood pressure. So they're going to secrete renin in order to increase blood pressure. We're also going to have secretion of epinephrine and norepinephrine. This is going to stimulate the sympathetic nervous system. We learned sympathetic nervous system will make your heart beat faster. We have low blood pressure, and so by getting our heart to beat faster, we're going to increase what's called the cardiac output, which is essentially just how much blood our heart is pumping. Whether that be from pumping a larger amount at a time or just pumping faster. We're also going to secrete antidiuretic hormone from the hypothalamus and posterior pituitary, which will cause vasoconstriction. If you have less water, make the hose smaller. That'll bring the pressure back up. And then finally, there's atrial natriuretic peptide. This causes vasodilation of the heart atria. And so we're actually going to make parts of the system larger. But you make that larger, you're going to lower blood pressure. So antidiuretic, vasoconstriction, atrial natriuretic peptide is vasodilation. This, I realize this means nothing to you, but what I will point out, and that natria is in relation to natrium. Look at sodium. Sodium up here, its symbol is Na. That's from natrium.
A form of
And so this is actually going to control sodium. Sodium is a huge, huge factor that controls how much water is in our bloodstream. If you have more sodium in your bloodstream, you have more water. That's why people with high blood pressure need to avoid sodium. If you take in sodium, you're going to get more water. If you bring in more water, your blood pressure is going to go up. If you keep the sodium in your bloodstream down, you keep the water in your bloodstream down, so your blood pressure stays
So
down.
what if you have low blood pressure? Do you need more sodium?
You can, yes.
Sodium.
Oh, good, 'cause I love salt.
Well, my guess is, if you have low blood pressure, there is a physiological or pathological reason for that, and so you're probably better off treating the cause than eating a bunch of
French fries.
Burgers and fries?
Chips.
all of them together.
Ew.
Yeah, or just yeah, eating
water.
salt out of the shaker.
Salt water.
Yeah, just drink straight up salt water.
But here we see a control of our blood pressure. And so here, something is going to happen. Some sort of stimulus is going to decrease our blood pressure. Doesn't matter what it is. Something is causing our blood pressure to decrease. Let's imagine we get some sort of, we get in an accident, we're bleeding. If we bleed, we lose blood volume. And so the rest of our body is getting less and less blood. And so the blood pressure is going down. So the baroreceptors are going to realize the blood vessel is constricting. As the water goes away, the blood vessel is going to constrict. Just like a water balloon. As you let water out of a water balloon, the water balloon gets smaller and smaller. The baroreceptors will notice that, send a signal to the brain. Medulla oblongata will release the norepinephrine, the epinephrine. It will also cause the adrenal medulla to release hormones, which will cause the heart generally to beat faster and the blood vessels to constrict even more. That water balloon will only get down so small. Even a blood vessel is not going to be flat. Even an empty blood vessel won't be flat. It will still be circular. So you can continue to constrict it if you get a signal to do that. Once that happens, blood pressure starts to go back up. Your baroreceptors notice that, and they'll send the signal back up to the brain to stop what you're doing. Keep it where it is. So if you go to the hospital, they're going to check your circulation. And they do it a couple of different ways. Number one, they're going to measure your pulse rate. A resting pulse rate for a healthy individual is about 75 beats per minute. But that's not like if you're not 75, you're bad. Okay? There is a normal range. And so as long as you're close to that, you're going to be okay. And actually, if you are in very, very good shape, you may be very, very low, but that could be a good sign. If it's very, very low, it could be a good sign that you're in good shape, or it could be a bad sign that there's something wrong. So you really have to take into account what is the physical shape of the patient you're dealing with. They're also going to measure the blood pressure. The blood pressure is just a measure of how much pressure is pushing out on the blood vessel walls. And when you take blood pressure, you know you get two numbers. You get systolic blood pressure and diastolic blood pressure. We learned systole and diastole last week. So systolic blood pressure is going to measure the pressure during systole. This is during ventricular contraction. So if you look at blood pressure numbers, the first number is usually, hopefully, higher than the second one. That's because it's measured during contraction. It's during that spike. The diastolic blood pressure is going to be measured during ventricular relaxation. So this is the resting pressure. So a normal blood pressure in a young adult male is no more than 120/80. If you were anything other than an average young adult male, your normal blood pressure is not going to be 120/80. And so there are charts that say what a normal, yes, they're on paper, which is normally rectangular in shape. And so you can look it up and you can see what the blood pressure of a patient is supposed to be. And of course it's going to be a range, but if someone is outside of that range, you know you may have an issue. Either too low or too high. Maybe only one of the two will be too high or too low. And that's going to mean something versus whether the other one is too high or too low. So what I just erased was a very, very basic idea of blood circulation. Heart, arteries, arterioles, capillaries, venules, veins. Back to the heart. We have a whole bunch of those loops. It is not just one loop that goes through the entire body. We have a bunch of loops. And so each loop is called a circulatory route. And there are two major ones. Of course, each one has sub-layers. But the two major routes are the systemic circulation, which is going to be the blood coming from the heart to everywhere in our body except the lungs. And then the pulmonary circulation, which is the blood coming from the heart to the lungs and back. And so there's heart, lungs, and back, which is the purpose of that. The purpose of that is to oxygenate the blood, to then turn it around and send it to the systemic circulation. And so in the heart, we have two atria, two ventricles. One pair is for this, one pair is for that. This pair works, blood comes back, it gets transferred to this one, and then it gets pumped out to every place else in the body. All of the systemic arteries come off of the aorta. The aorta is a gigantic blood vessel coming out the top of the heart, and then immediately then starts branching. And so you get all of the arteries starting to come off the aorta. As you come out of the heart, the aorta starts to go up. And so believe it or not, it is called the ascending aorta. It gets to the top, it starts to bend back down. It's called the arch of the aorta. And then when it starts to come back down, unfortunately it's not the descending, we get the thoracic and the abdominal aorta depending on where it's going. So here we have the heart. And so this very large red blood vessel here is the aorta. So the ascending aorta is coming out of here. And then as soon as we get away from the heart, we start to see arteries coming off. But the aorta itself arches, starts to come back down. So now we have the thoracic aorta. And then we continue down, and then it becomes the abdominal aorta. And then you have all these branches starting to come off. And so we have an artery. This is an artery that then starts to break off arterioles. We're going to come back to this in the lab. We're going to learn some of these specific arteries and veins in the lab. So the oxygenated blood is going to lead to the arteries of the systemic circular system. And it's going to return in the systemic veins. Just like all of the blood for the systemic system leaves through the aorta, all of the deoxygenated blood comes back in through the superior vena cava, the inferior vena cava, or the coronary sinus. And once you see a picture of this, it's going to make complete sense. And then these three things are going to empty into the right atrium. So here we have, We're not going down, we're